All right, we're back after a technical break. All right, so we were talking about drillers' logs and the kind of information we can get from them. The main things that we get are well construction and lithology. And then also we can get information on where and when and how much water the drillers were able to pump out of the borehole. Let's see if I can find that on our driller's log here. Doesn't look like we have information on where and when or how much water we got. But this flow information is often contained here in well test data. So there's aquifer test data or Baylor test or pump test. A bunch of different ways they sort of get some information on the flow. We're going to look at what those all mean here in just a second. Maybe I was just trying to find an example of a driller's log that has some information on the flow, but they don't really have it here. So let's look now. Let's move to understanding what we do now that we've got a hole in the ground. Okay, so we've drilled a hole. We've looked at the driller's log, and we have some information about the local geology. And so we're able to start building our conceptual model, which in this case, we've got, say, a bunch of alluvial material and then bedrock beneath it. So the next thing we need to do, and that we talked about in our conceptual problem of figuring out the groundwater streamwater interactions at the stone container site, is to now start characterizing the aquifer for its hydraulic conductivity, for its storativity, and other hydrogeologic parameters. And the primary way we do this is by perturbing the aquifer and watching its response. The principal way we do this is through pumping the aquifer and then observing what happens to the aquifer when we pump it. So is my audio working okay now? Yeah, better? Okay. All right, so okay, good. All right, so let's go ahead then. All right, so we're going to start talking about the response to pumping, a response of an aquifer to pumping. And pump tests are sort of the gold standard for looking at hydraulic conductivity and storativity in a well or in an aquifer. So here's the basic idea. Let's consider a cross section here. So here's my land surface. Draw some grass. All right. And we've now drilled a well. And we're going to we're going to start by thinking about confined aquifers because they are the easiest ones to deal with. And then we will talk about the difference between confined aquifers and unconfined aquifers. So let's say we have a well. All right, we've drilled it. And let's say this is bedrock beneath here. And our well is screened. So this is the symbol for screen. My well is screened over the entire thickness of my unconfined aquifer. All right, and the water level here in my unconfined aquifer starts out here. This is the head, H naught, before I start pumping. All right, it's above the confining layer, and I've got a fully saturated confined aquifer down here. All right, and I'm screened all the way across it. The basic idea is this: once I start pumping, so we start extracting water. All right, we start pulling water out. Then in order for me to induce flow to my well, I have to drop, once I turn the pump on, the water in my well, the water level in my well will drop. All right. So this might be H1. All right, the water level inside my well after I turn my pump on. And let's also we started off in the water level in my aquifer, no matter where I was, would be equal to this H naught. All right. So if I drilled a well over here, let's say I have another well over here, screened. All right. It would record the same H naught before I started pumping. All right. I start pumping, the water level in my well drops, and then this water level drop will propagate away from my well with time. So this would be, say, time 1. All right. Sometime later, this water level change has propagated out into my aquifer some distance. And the longer I pump, the farther out this water level change will propagate out into my aquifer. So this might be time 2. All right, so this is looking at it in cross section, and what you see here is this shape that is the cross section of a cone. All right, with the center being the pumping well and the radius of my cone extending out here to the point at which there is no more drawdown. I'm back at my original water table height. So this would be the radius of my cone at time 1. And then this would be the radius of my cone at time 2. All right, so there's a couple things. This thing here gets called my cone of depression. And it will expand away from my well until the amount of recharge or water coming in from the sides is equal to the amount I'm pumping out. So cone of depression will expand with time. until the recharge that I'm adding to my system is equal to the amount I'm pumping.
Do we assume that H1 is no longer changing? Or that can still keep on changing, can't it?
H1 can keep changing. Yep. It can be very complicated. So most pumps tend to operate at basically a roughly constant flow rate given a constant pressure. So generally H1 will drop to a pretty constant value. But when we do a test, we'll often regulate things like we'll regulate to make sure the discharge is constant, in which case H1 will sort of get to a constant spot because the pump's efficiency will basically dictate what the height is in order to get this discharge.
Right.
We're going to say for now that H1 remains the same.
Okay.
All right. So when I get this cone of depression, all right, my groundwater will flow from this higher head to the lower head. And so I get groundwater flow moving in radially to my well, all right? And it will only move from this point here where there's a gradient in head, right? There's no gradient in head past this point right here. So my groundwater flow will only come from the point where the head gets less than the initial head. All right. So this radius here, we call this the radius. This is the radius from which I'm pulling water, from which water is moving. All right. We call this the radius of influence. And this radius of influence gets larger with time, unless recharge is equal to pumping, and then it stays the same. And then this flow is radial, so it's coming from all directions towards our well, so we have radial flow.
Sir?
Yep.
So you're pumping, right? You have the initial drop, and then after a while it gets to T2, and the water flows in order to counter the pumping, and it only goes for a certain distance.
You're only pulling water from a certain, you can only pull water. The water can only move if there's a gradient in head. So you're only pulling water from this point here, like at time 2, you're only pulling water from as far out as my cone of depression reaches. So the water movement's only from this zone in. Out here, it'd still be stagnant because I'm at H naught, all right? So you're only pulling water from where the cone exists. All right, and it comes from the aquifer and into our well.
Okay, so is that how you can the water coming in, that's what stabilizes the H1 because their pumping out is going to be the same as the water rushing in to fill that void.
Roughly, yeah, you could think about it that way. The pump can only, the bottom line is if the discharge out of the pump is the same, this head inside the well is essentially got to be the same. The pump has a certain efficiency. I don't want to get too far in the weeds with, there's a whole bunch of different kinds of tests you can do. A constant pressure test, which is you keep that head constant and you vary the pumping, or you can do a constant pump rate test. That's generally what we're going to do. The differences here for us are not big. So the head's going to be roughly the same in the well and the pump rate will be held to a constant. All right, let's look at in cross. So this is cross section. Now let's look in map view what this radial flow looks like. So here's my well. All right, and I'm pumping out of my well. I'm going to draw now some head contours. And let's say this is at time 2. So I'm going to draw some head contours here. So at my well, I'm at H1, right? And then I've got radial head contours that if I was a good artist would be perfect circles around my well. And this final contour here would be H naught, all right? And I'm gonna draw a flow net here. I've got radial flow, so orthogonal into my well here. All right, so this is what the cone of depression looks like from map view with potentiometric contours. It would go from H1, which is lower, and then we'd come out here and come out to our H naught, and we have flow here towards our well. So this is cross-section view. Or this is map view, sorry. Looking down on our system. All right, let's define a few things. So as this cone of depression gets bigger and bigger, so here now I'm at, this is T3, all right, so it's continuing to expand. Whoa. All right, and now my water level inside this well out here, let's call this radius here RO, the radius, how about this, R obs, the radius of my observation well. And now at time 3, the head in my observation well has dropped. All right, to H obs, let's say. So it's dropped this distance. All right, we're going to define an important variable for us right now. We're going to define S, which this is little s. So I'm going to put a bar over little s. All right. Little s is the drawdown. All right, and what drawdown is equal to is H naught minus H obs. All right, all of that is the distance here that the water level has dropped. All right, it's just a difference in head from my observation well. So it's the initial head minus the head after some time. So this is the drawdown. H naught minus H obs. All right, so the bottom line is the shape, how far out this cone goes, how fast the cone moves out, is a function of the hydraulic conductivity and the storage of our aquifer. All right, so the whole idea of pump tests is to pump at some known rate and observe how this drawdown cone moves out. All right, and the shape of that cone gives us some indication of the aquifer properties. All right, so we're going to consider first this, this scenario where, so let's think about a steady state. We're going to move to steady state. So we're going to consider a steady state cone. And this means that the amount I'm pumping is equal to the recharge of the aquifer. All right, so I'm pumping out exactly how much water is entering the aquifer. All right, and my water table configuration reaches a steady state. All right, I have a constant drawdown cone. So this implies that my drawdown cone is stationary. All right, in that, so if I have steady state, so first of all, let's write the general governing equation for a radial flow. It is SS dH dt is equal to,
Shouldn't that be 0 for steady state?
let's start with general and then we'll go to steady state. You're right. You're right.
Okay.
Let's start general and then go to steady state. And I'm going to
Okay.
use all right, where T is the transmissivity, that's K times B. All right, this is, so when I can make a change of coordinates from XY to radial coordinates. All right, and when I do that, you just end up with this 1 over R extra 1 over R dH dr. But the bottom line is this is the governing equation. This is for radial flow to a well. If my T's out here, what does that mean in terms of, first of all, let's ask a couple questions. So T's outside of a spatial derivative. So what does that mean for my aquifer? What assumption have I made? If my T's inside the spatial derivative, it means that my transmissivity changes with location. So if I bring it out, I'm saying it's constant with respect to space. So what does that mean?
Isotropic?
Close, but no cigar.
Homogeneous.
Yeah, homogeneous. All right, so let's so Amanda suggested isotropic. Let me ask you this. How many dimensions does this equation have? How many spatial dimensions?
Looks like 2.
So
One.
Mark thinks it's 2. Why would you say 2, Mark?
1 second. Your the pictures are in. It has 1.
Yeah, there's only radius here. R is the only spatial direction. That's why we make this change of coordinates. All right. So we turn this 2D field into a one-dimensional field. It's only a function of radius. So important point, this is a one-dimensional flow field. All right. And in that case, Amanda, does it make sense that it's to say it's isotropic or anisotropic?
Yeah, not really. Doesn't matter.
No, it doesn't matter, right? So we'll say it's isotropic, but it doesn't really make sense because it's 1D flow. All right. Now, if, as Andrew correctly pointed out, I'm considering a steady state cone, then this guy goes to 0. All right, and my governing equation becomes this, d squared h dr squared plus 1 over r dh dr is equal to 0. All right, we can solve Darcy's law for radial flow. All right, and I don't have time to go through that full solution, but let's just look at, so if we solve Darcy's for radial flow, to our well, we can come up with a solution that gives me, we can back out what we call the team equation. Which is this, transmissivity Q over 2 pi H naught minus H1, the natural log of R 1 Oh, this is not H naught. Let me. So let's look at a drawdown cone here. So in order to use the time equation, we're considering, so here's my pumping well. We're saying we've got 2 observation wells. All right. So here's my constant cone of depression. All right. And this one has a height of, this is H1. It's at a radius R1. This well has a head of H2 and a radius of R2. All right, and so we're looking at the shape of the cone from these 2 wells, and we can estimate the transmissivity of our aquifer by using these 2 heads and these 2 radiuses of these 2 heads, all right? So we need 2 observation wells around our pumping well. That gives us some measurement of the shape of our cone, all right? And we can back out the transmissivity. So this is our team equation that only works if we're at steady state, all right? If our cone is no longer moving, we can use it and 2 measurements of head in a well in 2 different wells to estimate our transmissivity.
Hey, Peyton, does it matter which well is the H1 or H2, or is H2 the one that's closest to the observation well?
H2 usually has to be yes, it does matter. Well, no, it doesn't really matter. It shouldn't matter. They just need to be, R2 and H2 need to be matched. The numbers, I generally think of H2 as being farther away because then this keeps this positive. But it doesn't matter because the natural log, if this is, if H2, yeah, it doesn't matter. If one's closer than the other and the heads, if this one ends up negative, then this one will end up negative. So it shouldn't matter. Okay, so this is our first, simplest method to try and get at transmissivity if we've got a steady state cone. But the bottom line is, in life, we never have a steady state or rarely have a steady state cone. So we're going to look next at transient flow and the Tice equation. All right, now the Tice, or the Tice solution. This Tice solution is going to end up being our basis for understanding well response for any other kind of aquifer. But let's write down right now explicitly what our assumptions are for the Tice equation. So make my font bigger here. All right. So here are our assumptions. All the water we pump is from storage. All right. So that means there's no recharge from our confining layer, no recharge from anywhere in the aquifer. We're only pumping storage. Our aquifer is homogeneous and infinite in extent. It is confined. It is constant thickness. What else? I think that's it. All right. So let's look at the let's look at our general equation. Ah. All right. This term here, storativity over transmissivity, has a special term. This is called the hydraulic diffusivity. And it is basically a measurement of how easily a change can propagate through our aquifer. So how well a change in head this is actually 1 over the hydraulic diffusivity. All right, so the hydraulic, this is actually 1 over the hydraulic diffusivity. So the hydraulic diffusivity is actually equal to the transmissivity over the storativity. So this is the inverse of hydraulic diffusivity. So this would be the resistance. This term here would be the resistance to change. To head change. Well, what does that mean? Let's think about it. if my storage, if I have a lot of storage, then my resistance to head change would be large. That means I could, if I have a lot of storage, I've got to pump a lot of water before I'm going to drop the head. All right. If my transmissivity is really high, I'm going to have a low, if my transmissivity is really high, I'm going to have a low resistance to change. That's because the transmissivity will propagate that head, or the water can flow from a very far distance away. If I have a really low transmissivity, even if I've got a big head gradient, the water can't move fast, and so I won't see head change very far away from my well. All right, so this term, this resistance to head change is, you'll actually hear more of it in the so 1 over the hydraulic diffusivity, which is how well a head change propagates. But they're essentially the same thing. They're just a measurement of what we might expect, or a characteristic of how we might expect our aquifer to respond to a head change. So when we drop the head in the well, how well is, or how easily does that cone of depression propagate through our aquifer? All right, so we got a governing equation. I'm going to add some boundary conditions. That is that our head is equal to H naught when our radius is equal to infinity. All right. The other is that an initial condition that H is equal to H naught at T equal to 0 for all R's. All right, so we start off so this, let's look at what we got here. Here's my land surface. I've got this confining layer. Here's the bottom of my confined aquifer. I am pumping. Oh, this is another assumption that I need to put down. I'm screened over the full thickness. So this is another actually really important assumption. Screened over the full thickness of the aquifer. Okay, so here's my unconfined aquifer of infinite radial extent. All right, I'm pumping at this constant rate QP. My head, before I start pumping, this is my initial condition. All right, and that this at x equals to infinity, my head will be constant in my aquifer, all right, at H naught. All right, sometime after I initiate pumping, I drop the water level here, and I've got this cone of depression. All right. And we're going to look as if, again, like in the time equation, we've got two observation wells at different distances. And they are measuring the head, or the head in each of these wells at different distances. So this one would be R1. This one would be R2. Okay, so what we're gonna, we have a, this would be at some time. This is at T1, whatever time that is, all right? This, our drawdown well will be, our drawdown cone will be propagating through time in our aquifer, all right? And we are looking, we have two observation wells at two different distances away from our pumping well. And we're looking at the head in those two wells at different distances. All right. So we can derive an analytical solution to this scenario with these boundary conditions and this governing equation. And so this analytical solution for drawdown at a well. All right, this is the Tice equation. And it looks like this. S, the drawdown, is equal to the pumping rate over 4, that's a P, pi T the integral from U to infinity e to the minus x over x dx. All right. This integral here is an important integral. And in groundwater, we call it the well function.
Are those supposed to be X's or R's for distance?
They're supposed to be x's, and they have
Okay.
nothing to do with the distance. All it is a variable.
Okay.
So if you want to know the well function, W sub u, you put a u in here and you integrate from that u up to infinity across some variable. I could have put anything in here. L,
Okay.
P, all you're doing is integrating e to the minus x over x dx from u to infinity. All right. This integral you cannot get analytically. You can't solve it, and so so we call it the well function, and there are tabulated values or there are numerical programs that will give you the well function for a given u. All right. So what we're going to do, we write the Tice equation. In general, in practice, we write the Tice equation this way. S is equal to QP over 4 pi t w sub u, where w sub u is given by this integral, and in general, we're going to look it up or calculate it with a computer. And u, we have to be able to calculate u. U is r squared over s r squared s over 4 t transmissivity little t time. All right, so in general, to calculate the drawdown at a well, we first need to calculate u, so we need the radius, the radial distance of the observation well from my pumping well. I need the storativity of my aquifer. So for an unconfined aquifer, that is SS times B. Sorry, this is the, yeah, SS times B. I need the transmissivity and I need the time. All right. If I put that in here, I can look up W sub U. I can then use again the transmissivity and the pumping rate, and I can calculate the drawdown at that well. All right, so let's think about an example problem here. I've got a pumping well. Pumping at QP. And that is equal to 400 meters cubed per day. All right. And I've got an observation well. 1,000, let's see, let's do 100 meters away. All right, so my transmissivity of my aquifer is 1,000 meters squared per day. And my storage coefficient is 8 times 10 to the minus 5. So what is the drawdown? At A. Now, in order to solve this problem, we're going to need to know the well function. So here somewhere. Somewhere I have the well function. Well, I know where I got it. Okay, so here's how we have to solve this problem. The first thing we need to do is to calculate U. All right. Then we'll get W sub U. All right. And then we will calculate the drawdown. So the first thing I want you guys to do is calculate U. So what is U? So you guys calculate U for me. Oh, I want the drawdown at A. You need some more information. After 48 hours. All right, so what is U?
Did you give us R?
Yep.
Sir, I
Yeah.
have 1 times 10 to the negative 4.
So Mark Reel's getting 1 times 10 to the minus 4. Anyone else got a number?
I got that number as well.
I got the same thing.
Okay, so we have a quorum. So U is equal to R squared S over 4 big T little t. So R squared, well, R was 100 meters squared. S, 8 times 10 to the minus 5th. 4. Transmissivity, 400 meters. Oh, wait. Transmissivity 1,000. And the time would be 48 hours, which is 2 days. All right. And I think if we get that, U is, what was it? 1 times 10 to the minus 4.
Yes.
All right, let's look at units here. Meters squared, those cancel out. 1 over day times day, those cancel out. So U is unitless. All right. And we get 1 times 10 to the minus 4. All right, so now there's a few different ways we can get the well function. There are, like in your book, there's a table where they basically have tabulated values of WU. So for every, you in that table, you'll say, oh, U is equal to 1 times 10 to the minus 4, and it'll give you WU. And I've written a well function. I've written a well function program here in Python. So we should be able to do W sub U using this. All right, so well function 1 e to the minus 4. It is 8.633 all right. So now step 2. So step 2, get W sub U. Step 3, calculate drawdown using the Tice equation. All right, so now we're gonna calculate drawdown using the Tice equation. You've got W sub U here. You've got transmissivity. You've got the pump rate. So what is my drawdown?
Or what is WU?
8.633. Let me rewrite the Tice equation here.
So I have 0.275.
All right, Mark's got 0.275. Anyone else got a number?
That's the same one I have.
0.275 what?
Meters.
Meters. All right, so my drawdown after 48 hours at this well is 0.275 meters for 27 centimeters. All right. Okay, so the Tice equation gives drawdown at a point at a distance r and time t important given S and T, given my aquifer parameters. All right, so what I wanted to do with the last 4 minutes is talk about a little bit about forward modeling and inverse modeling. All right, so the Tice equation allows us to predict, so we can predict drawdown S given the properties of storativity and transmissivity, right? So if I know already what my aquifer parameters are, I can model the drawdown at a point, all right? So we call this our forward model. And the basic idea is, given parameters, all right, in this case, S and T, predict drawdown. All right, so my forward model is, given my parameters, predict drawdown. And that's what we just did, right? We said, all right, I've got a forward model. I gave you the storage and transmissivity. You predicted the drawdown. All right. So in math, we might write this: my model is some function A of M, my model parameters, and that's going to give me my data or my drawdown. So this is my model function. This is my parameters. And this is my data. All right. That's my forward model. Now, the inverse problem is to go from taken data, given data, so given my data here, which would be drawdown, all right, calculate parameters. All right. So in essence, we're going backwards. We're taking, instead of predicting drawdown, we're going to take drawdown and we're going to predict or calculate what parameters I needed in my aquifer to give me my observed drawdown. So in math, this gets written like this. My model parameters, A inverse D, where A inverse now is my inverse model. It takes my data and maps me back to the parameters that I want, all right, that I need to produce that data. Okay, so essentially what this is matching my model. This is matching modeled and observed data to calculate my parameters. And this problem, this inverse problem, is super common throughout sciences, all right? And it is not as straightforward as you might think to calculate this A inverse, all right? And there's, in fact, whole fields of study on how you might actually calculate this. We're going to look at some, we're going to stay with simple models where we can calculate this or get around having to calculate it, which we'll do on Thursday using curve matching. But at its bottom, at its most base level, all we're going to do is match modeled and observed data by finding the parameters that basically give us a predicted data set that best fits our observed data set. All right. So if we take a forward model, we invert it, and we get the best fit parameters. And that's what we're going to be doing. That's what aquifer characterization is all about. We're going to observe drawdown. We will fit some model as best we can to that observed data. And those are our estimated then we're going to fit it by varying storage and transmissivity. And those estimated storage and transmissivities are our best fit values for our aquifer. All right. And we will start doing that on Thursday. We'll play with it both by hand and start to use some Python functions that I've written to do this in a more formal mathematical way. All right. So if by Thursday you can't get Python installed on your computer, email me, say Wednesday afternoon, and we'll try and figure it out. All right, so I want you guys to get Python installed. There's some functionality that I've written that'll allow us to take data sets and invert them and find storage and transmissivity. Holly asked me, does Jupyter Notebook work? Yes, if you've got Jupyter, then you can run these utilities. And if you've got Jupyter, you have Python. It's a little easier, I think, if you can get Spider, because I like working with an integrated development environment, but you can totally use Jupyter Notebook. All right. So I have office hours starting, so I'm going to go get some more coffee, and then I'll start up office hours if you have any questions. Otherwise, I will close off this lecture for the day. All right, have a good rest of your Tuesday, and we'll talk to you guys later.